Hey, what's up, guys? Since we have a holiday in this Friday, but I think we still need to make a video, right? We still need to make a lecture, otherwise we don't have enough time to cover a whole class. So I will try to give two lecture. Each one is like 40 minutes, so that we go through these backgrounds, and I will also upload PowerPoint that so that you can just read. Okay, okay. So recall that previous we talked about this so-called Bell inequality and the density matrix. Since we are gonna talk about the quantum circuit model, so we will first or discuss the quantum computing. So we need to dis discuss some basic background of computer science and give you some some story. And just so this is so I would say this is just some motivation. Okay, uh, so motivation is that we know that if we have two quantum computer that's a Bell inequality, that we can be classical by playing the so-called non-local game like SH game that we already described. So one can view this as one type of so-called quantum supremacy. And but what about there is only one quantum devices that in the universe? Okay, so this answer may be so-called this is why we need to discuss like some quantum computation. But in order to define this, right, to define what quantum computation means, we need to first define what computation no really means. So we need to first define what classical computation. And after we define it, then we can define a similar thing called quantum computation or basically quantum computing. And this is a huge area that will motivate so-called computational complexity. Oh, sorry, there's a typo here. Okay, so the fundamental question is that what's computational really means, and what's the so-called classical computation and the quantum computation, also what efficient means, what languages mean, what algorithm means. So there are many fundamental questions that I need to first describe. Okay, so in computer that yeah, this is some codes, and what in ideas what the main problem in the computer science so-called algorithm basically is core computer science. So the idea is we will give a precise definition, but I will first give you some intuition. So basically some recipe for a task. And but we need to answer we need to give a computational model such that when I say that this problem can be solved by some computer, I need to first define what computer means, right? So the idea the main tool of what we use basically what people use is so-called Turing machine. Okay. And uh, what resources are required for a computational task is fundamental question in the computer science. Like we need to find two parts, right? So first is that we need to find explicit algorithm for a specific problem like sorting, right? So sorting basically means that if I give you a array, let's say 3, 5, 1, 4, this is inputs, and you have to write down a code. You have write down a code such that it gives you the output, and then you sort this, so you get 1, 3, 4, 5, right? So this is and you need to hopefully you can find a the quickest way to do this. And there are various way. If length is n, then you can take like n log n using the so-called merge sort or other specific sorting algorithm. And hopefully you can prove so-called limitation. For example, one can prove that if there's no other information that n log n time swap n with n log n times the best that you can do. So I encourage you to find why this is true. Okay, and why we study so-called classical computer science is that we need to use there's a so-called reuse concept that's a for some techniques, and you hope using these techniques move some techniques in quantum. And then you have some comparison baseline that once you know quantum supremacy, you better know some classical complexity so that you can compare the quantum resource and to classical resource. Okay, and maybe you can think about think like computer scientist. Hopefully, this will give you some very interesting idea. Okay, so the chapter structure, I will first describe the model, Turing machine circuit model. Yeah, so it's just an introduction. And I will give another PowerPoint, basically another like 40 or 30 minutes, describe the computational complexity. And so hopefully this gives you a broad view of computer science relative to quantum. Okay, an algorithm that I already said, right? For example, like sorting, and this is another adding two numbers or so-called Euclidean like greatest common divisor algorithm. I give you two number. What's the good way to give you to quickly find this GCD? Okay, so actually the history comes from the so-called Hilberts, right? So Hilbert can be viewed as a like most greatest mathematician like in the among history, right? So he proposed like 23 different question that involving like physics and philosophy or into like mathematics. Some of them are very abstract mathematics. Like the first question is that whether so-called continuous hypothesis, whether there's a third kind of infinity between the real and rational number. So this is somehow like if you learn some abstract maths or you do some real analysis, then this is the first question. But there is a other question, right? So for example, one of the Hilbert, I remember is 6 or something or 8. So Hilbert asks whether there's an algorithm. I give you a polynomial, and you can check. There's an algorithm who maybe you can check whether this polynomial has integer solution. Right. So for example, whether there's an algorithm that if my input is xn, yn equals zn, this is famous Fermat-Less theorem. And what Hilbert asks is that, oh, if I give you this, you input this as a computer, right? Is there an algorithm that tell me that this problem has a positive integer solution or not? Let's say you fix n to be 100. Okay. So this is what this is called basically I mean I don't know how to pronounce this, but indeed this is just asking about the algorithm question. Okay, so Hilbert challenge is there basically this is you can prove that okay, it turns out that all the computer problem can be reduced to finding some positive integer solution. Okay. So the answer what Aaron Turing gave is no. Okay, no such algorithm exists. But in order to do this, you need to first define what computational model is, right? So the interesting thing is that this is actually proposed by a mathematician and start with I would say that the beginning of 20th century. Okay, so Turing machine. Okay, so I will describe the Turing machine, but okay, but actually the model of Turing machine is highly I mean easy to state, but if you want to define mathematical rigorous, it would be very complicated. So I would just say some idea, and it's fine that you don't know the definition. You just need to have the intuition. Okay, and after that we will describe the so-called circuit model. So I would say these are classical models. So circuit models are easy to understand. If you have some electronic engineering background or you do some logical design, that I would believe that circuit model is easy to understand. Okay, and okay, so and actually, Turing and Turing model equivalent in some computational power in some I would say in some situation, but the detail I will omit. So I will basically hope you to just understand the idea and believe they are the same under some condition. And indeed, that multi-model provide different perspectives, but yeah, this is somehow like a very detailed thing. So I would say what's Turing machine. So maybe we first okay we first see the plots. Okay. So that would be simple. Okay, so you imagine that the Turing machine Turing machine definition is there's a tape, which is infinite, right? So this is there's a tape, And this is there is a starting point. So you start with one side and there are infinite. Okay. And there are some alphabets on the finite alphabet. It's finite, right? Because if you type a program, then you can only type the English alphabet from A to Z. So this is 26 alphabets. And you can also type the numbers, some common, right? Some other, like maybe type some Greeks. Okay. But it's always finite, right? So there's only finite alphabet on each tape. Sorry, on each cell of this infinite tape. And then there's a so-called computer program, which is this computer program has a so-called has a head. So this head will read the tape, the alphabet on the tape, and then you will do something, right? Either you will move left or right, or you can like write something on the write something on the tape on the particular cell and then keep moving. So there's a this computation this program has read some inputs and do some outputs and move left or right, simply speaking. And after some finite move, and there's a special cell which is called a terminate. So once this program meets the terminate cell, and it will terminate. Sometimes, okay. And there's a case that maybe move keep going to the right, never terminate. Yeah, this is also doable. Okay. So yeah, this is the the definition. Okay. So mathematically, we will first yeah, so these are like program finite state control. Basically, you imagine, so there's a mindset in the or some status in this program, and then there's a tape, infinite memory, and there's a finite symbol. Okay, and you can read or write. Okay, you can read a tape, read a cell, and write something on a cell. And the finite control, so there's only finite because you only have finite memory, right? So you have finite status on your program. Okay, so you have state Q1 to Qm, let's say fix M, and then some start state, some hold state. Okay, and yeah, so you don't need to know the whole mathematical definition, but just these are just written on textbook. So infinite number and infinite tape, and you have some tape height, and so program will just form by some alphabet that once you read it, and it will do something, go left and right. Yeah, the definition. And sometimes you will hold. Okay. So I will skip this. And there are like different Turing machine. For example, you can define Turing machine with two tapes and two different heads. Okay, and you can so this is somehow like this is the definition. And then there is this is in some museum, right? There is a physical Turing machine that one can construct. Okay, so mathematically this tape is infinite, right? But in your computer, your computer has don't have infinite memory, right? So actually your computer is less power than this Turing machine. Okay, and indeed that the single tape or two tape Turing machine are equivalent, and there is a so-called universal Turing machine. So I encourage you to read the textbook box 3.1 that there is a so-called universal Turing machine, which this Turing machine will read its input is a Turing machine and input, and it will simulate this Turing machine on this input. Okay, so let me just write down. So there's an idea so-called universal Turing machine. It will read one Turing machine and some inputs, and it will simulate this Turing machine on the input X. And then you can also define so-called randomized Turing machine, basically, which is a Turing machine which it can throw a dice or throw a coin. Okay, you can prove that throw a coin is that throw the dice is, but you will basically throw a dice, and then once it's heads, you will do something. Once it's tail, then you will go do something. Okay, so in this case where this Turing machine terminate holds at some point, it's basically become a probability distribution. Okay, so it's basically randomized. You can throw this Turing machine can throw the dice. Okay, and there is a so-called formal definition. You don't need to read. You don't need to understand the detail. There's a finite, basically some alphabet, and then there's a so-called plain symbol, and some finite states, and some initial state, some hold state, and there's a so-called transition function. Basically, just a program. You just write, oh, if I see something, I do something. If else, I do something, else I do something. So it's the same as the program. When we write the C++ or Python program. Uh, okay. So yeah, this is just some example that I just encourage you to read it, but it's fine that if you don't read it. So take-home message is that Turing machine is a mathematical model that tries to capture the model computation. It has many variants, but usually the classical computing model is described by deterministic or randomized Turing machine. So indeed, that if one asks, well, what's the classical computation? Basically, it's a computation that defined to be use this classical randomized Turing machine. Okay, you can try to think Turing machine just a usual programming language like C++, Python, Java, and there's a multiple if and else. If you see it, you do something very intuitive. The math is complicated, so no, I believe no one remembers this definition. Okay, so once you have this physical or mathematical model on your mind, that you can define so-called languages. Okay, so languages is somehow well defined thing. So yeah, I mean everything is well defined. But the form language is basically some. So we first need to define alphabet. So we in this case that we assume that there's only 0 and 1. So classical bit. And a language L is a subset of all finite string. So you take a finite string, which is a set, right? You take subsets. That's it. That's the definition. Okay. So for example, you can take L to be binary even numbers. So there are basically the even number which has so you take the okay, so let me say this. So one can still say that language L now is defined to be number defined to be as a binary if its binary representation is a even number, is an even number. Okay, so for example, 0 means 0, this is 2, this is 4, this is 6, right? Okay. And then you can also define a more complicated thing. You can say my L is defined to be all the num x in binary, but represent a prime. Okay, so for example, 2 is a prime, right? So 1, 0 is inside these languages, 3 is a prime. So 1, 1 is inside these languages. And yeah, and you can say 5, right? So 5 is 1, 0, 1, and 7 is 1, 1, 1. Okay. So if I ask you how, okay, so this is a definition. So you just take subsets of finite binary string. Okay, subset. Okay. An algorithm basically is more intuitive. Given L, right? Algorithm A is simply a program Turing machine, basically a program Turing machine like previous Turing machine, such that AX will deciding L. So for example, if X in L or X belongs to L, then AX output 1. Otherwise, AX output 0. Okay, so for example, for these two, then I can ask, oh, you just give me a program such that you check where X is an even number. Or you may say, oh, this is simple. I just divide by 2, right? If it's divisible by 2, then it's even. Otherwise, it's not. But how about this primary, check whether given a number is a prime? This is a difficult question. Right? You might say, oh, it's simple, right? I just do a division, right? If you give a number x, then I just divide by 2, divide by 3, divide by 4, blah, blah, blah. If it's cannot be divisible, if it's not divisible by any number less than x other than 1, then I say it's prime. Okay, so this is a well defined algorithm, right? But it may not be efficient. And actually, it takes like I remember it's like 200 or 300 hours. Sorry, 200 or 300 years for people to check whether there's a more efficient algorithm on the checking whether a number is prime. Okay, and so one easy way to do this is just do 1 to up to square root of x. As I believe this is in your like high school algorithm. Okay, but this is this is so slow, right? For example, if your x is 2 to the n, let's say the length of x is n, then this number is close to 2 to the n, right? And the square root of x has 2 to the n divided by 2. So this algorithm actually takes an exponential time. If n is 100, then then it would be then it's impossible to do this algorithm, right? And indeed, there is a polynomial time algorithm to solve this prime, check whether a number is prime. Okay, so for the computational power there's an idea called Turing cities. So all intuitive computational functions are Turing computable. So basically, so once you define Turing machine, right? Then all the languages will be cut into two pieces. Some of them are decidable by the Turing machine. Some of them are not. Okay, and you might ask why? Maybe all the function, all the languages are decidable by the Turing machine. This is some interesting mathematical question. If you learn some real analysis, then the answer will be simple. Basically, all the deterministic Turing machine are countable. Okay, so number of Turing machine, or I should say, deterministic Turing machine are countable. Okay, the reason is that you can only because your code is countable, right? So you have some finite length and you do some finite alphabet, so it's countable. But number of languages is uncountable. And this is basically the same as number of reals are uncountable. You can try to prove it. This is some detail in the set theory, and I will not prove it here. Okay, but yeah, if you want me, if you guys want me to prove, then I can make a like 10 minutes proof in the lecture. But yeah, it's easy to prove. So accountable or uncountable, there's no one-to-one mapping. Okay, so so there are some very weird languages which you cannot compute. You cannot decide by Turing machine. Okay, so the problem which you can decide, which is decidable from Turing machine are people, most of them are we are interested. Okay, so now comes the interesting part. So what's quantum computation? Suppose you are convinced by Aaron Turing that classical computer, yeah, this is the picture of Aaron Turing. So if you believe that classical computation are defined by the so-called deterministic or randomized Turing machine in like 30 to 1930 and 94 to 1940s, then 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 you want to say, oh, I'm interested in so-called quantum computation, right? Because quantum mechanics are invented or basically developed also in the early of 90s, right? So you should somehow like maybe quantize the Turing machine. You can define so-called quantum Turing machine, right? This is somehow like the intuitive thing. Yeah, this is some more handsome figure of Aaron Turing. Yeah, indeed, there's a definition called quantum Turing machine in 90 and 92 that physicist this Paul Banff I sorry about his name. I don't know how to pronounce, but pronounce the article that first describes so-called quantum machine. You can find a paper here. Okay, and unfortunately, so if you want to define Turing machine, a quantum Turing machine, you need to somehow like make this transition function, make this program quantum, right? So it will be very difficult. Okay, so intuitively, such definition looks pretty unnatural and very hard to work with. And so in 1985, that David Deutsch, so Deutsch is a very like pioneer in quantum computing, which is like almost like close to Feynman. Further developed the idea of quantum computing by suggesting quantum gates. So this is somehow like indeed is the same as computational power is indeed the same as quantum Turing machine. But quantum Turing machine how to work with it, right? So we move Turing machine to the so-called quantum gate model. And this is the model that we are working with, or people are working with now. So now we can answer some fundamental questions. So what's the computational really means? The answer is Turing machine. Okay. What's the classical computation? Basically, classical Turing machine. Quantum computation, so we can define quantum Turing machine by heart. So we will use the quantum circuit model. And efficient means, okay, long story. So in order to do this, we need to define, there's a whole area called computational complexity, which is, I prepare another PowerPoint that It's not on textbook, but it's from my experience. So I will present in the next lecture. Okay, so we need to define a classical circuit model, right? Because we want to say I use a quantum circuit model, so I will first need to describe a classical circuit model. Okay, so circuit model, I would say is alternative to the Turing machine and the equivalent computation power, and more realistic, and I think more easy to understand. And I would say key for quantum computation study. So I think everyone knows what circuit means, right? So if you do some like double E or do some electronics experiments, then there's a circuit. So a circuit has basically each line is carry a bit, and there's a gate you can perform a computation. Okay. What do we mean by gates? For example, AND gates or OR gates or NOT gate that we will explain in detail. And right, so there are various gates. For example, this is NOT gate, this is AND gate, OR gate, it's the XOR gate. Okay. Okay, so gate is very simple. So for example, single bit input A through a NOT gate. So we will write as 1 plus A. Okay, so one NOT gate means is that it's very simple. If input is 0, then output is 1. If it's 1, then input is output is 0. So just flip a bit. Or basically you can see this is just X, poly X, right? So there's an idea called logical gate. So given any Boolean function, so any Boolean function basically its input is k length k0 length k bit string and its output is L length L bit strings. And the NOT gate is defined to be basically in this case k equals to 1, L equals to 1, and output 1 plus A. Oh, sorry. And there's a multiple inputs, and in the logic gate there's a much more complicated thing. You can provide a multiple input output gate, wires and gate, and then no loops allowed. Okay. Okay. No, so you cannot count. In actually you can do this, but yeah, but that's assumed you are not allowed to do this. Okay. Okay. So I will first review logic gate. And most of logic gate are 2 input bits and 1 output bit. So for example, NOT gate is 1 input bit, 1 output bit, but AND gate is 2 input bit, 1 output bit. Okay. So N is output 1 if both inputs are 1. This is basically logic AND, right? So AND means that both need to be true. And OR basically means that it's true if any one of them is true. Okay. And the XOR gate is special. Output sum of input modulo 2. Okay, so I would say this is usually also called exclusive OR. So I would just so the input if it's 0 0 is 0 0 1 is 1 1 0 is 1 1 1 is 0. So this is different from the OR gate, right? So in the OR gate this is 1, but for exclusive OR then this is 0. And then you can define a NAND gate. NAND gate basically you take AND and you take a NOT, right? So you just change it. And NOR gate just output NOT of OR. Okay. Hopefully this is obvious. And then the circuit model that so we have a plot, right? So I mean you don't need to remember this. This is just something from electronics. Okay, so this AND gate. Oh, by the way, use this straight line basically means 2 of them need to be true. And the OR gate is like somewhat smooth one that one of them output true if one of them are true. By the way, true is default to be 1, false is default to be 0. Okay, there's a code called fan out. This is fan out. You just take a bit and copy it to. Then do this. You just copy it. Okay. This is not doable in quantum computing, right? You are not allowed to copy a state. No cloning theory that we already proved in the class. You can swap 2 bit. Okay, so you can swap. Okay, and there's a so-called NCDA, so you can prepare some working bit. So for example, this is circuit, but you can say, oh, I do some 0 here. There's a 1 here. So I input some other bits. Actually, these are doable by like modern like electronics, like using MOSFET or like BJT, bipolar junction transistor. These are all the all the things that you learn into your basic electronics. So this is called NC lab bit, and you have fan out, and swap. Okay, so in order okay, so once we define all this, then we would like to study so-called universality of Boolean circuit. So the intuition is that okay, so you have some fundamental gates, right? These and or nots, and gate or not gate, right? So, but the question for you is to compose a complicated function using these elementary gates. And this is important because you hope you only do some particular gate in your engineering, so that any more complicated thing can be composed by using elementary gates. Okay, so we only care about the function which n input and one output. It's fine that you have n input and other m outputs, right? But you can decompose easily. So let's consider n input and 0, the one output. And the goal is to prove any Boolean function is computable using a few fixed gate. Okay, so this is the goal. So we want to say that whatever is complicated, it can be done by the previous gates at n or not x or whatever, right? Okay, so for any n equals to 1 base case, it's easy to prove. You can prove that any function from 1b to 1b can be composed by the previous one. Maybe that let me do this, right? So for example, if right, so there are actually 4 functions, right? Because either 0 can map to 0, 0 can map to 1, or 0 can map to 1, 1 map to 0. Okay, there are only okay, so these are oh sorry. So if yeah, 0 can map to 0 and 0 to let me just do this. So there is a function that 0 map to 0, 1 map to 1. So this is identity, right? So you don't need to do this. You just connect the wire. Okay. And if 0 map to 1, 1 map to 0, then you just take a NOT gate. Right? You just take a single NOT. Okay. And okay, so if everything are mapped to 0, then it's easy, right? Because I mean, yeah, you right, because uh okay, so if you start with either 0, then you map to 0. If you start with 1, you map to 1. You map to, I mean everything is set to be 0. But this would be simple, right? So for example, you can say x and with not x, right? So this is always be 0 because either one of it must be false, right? So the output must be 0. Okay, so you can compose with n and not. Okay, and similarly, if everything is true, then you can just do x or not x. So one of it must be true. One of it must be true. So basically, it's simple. There are 4 functions that you can easily do, or you can use NC. Okay. And the induction step is that I have the n plus 1 bit. So I assume that NB function can be computable by circuit. So this is my induction. So if I have 0, 1, n plus 1 to 0, 1, then I say f0 is defined to be f, the first bit is 0, and f1 if the first bit is 1. So these are NB function computed by induction hypothesis. I now have a figure 3.8 to compute f0 and f1 on less n bit. So this is I copied from Nielsen. Okay, so yeah, so this will be exercise. Or maybe we can prove it. So this is the f0 and f1, right? So you can imagine that if x0 is 0, then this is 1, right? And then this is 1, and then this 0 go here, 0. So this AND gate will always false, right? False. Will output 0 here, output 0 here. And so you can see this guy, right? This guy connected to 1, and this guy connected to f0. So this is f0. So 1 and f0 output for AND, right? So your 1 and f0 is basically f0. Because if f0 is 0, then it's 0. If f0 is 1, then it's 1, right? So this guy is f0. Now f0 and 0 XOR is always f0. Because it f0 plus 0, right? And similarly, so you can see that when this is 0, then output is F0. And similarly, you can prove that if this is 1, then output is F1. Oh, okay. Hopefully. And so circuit compute, so the induction finish it proof. Okay, so from this picture that we have some universal guy, right? So we need to use a NOT gate and gate, XOR gate, and yeah, so we have wires, right? Definitely. With some MCDA, we can copy bit, and we can swap in it. And yeah, so these are swap or something, right? So basically what we need, but elementary we need AND or XOR and a NOT, right? So we have like this some elementary tool. Let's focusing on four of them, right? So let's say we have AND, we have OR, and then we have XOR, we have NOT gate, right? It's here is AND and XOR, and then there's a NOT. Okay, so we have somehow like seems like we have four guy, right? I mean, so swap and wire, I would say is basically elementary. We don't need to care about. It's not gate, right? Okay, so wires is simply. For quantum circuit, it's more difficult, but we will explain later. Okay, so classical universal are not, right? We know it. Okay. There's an idea called Toffoli gate, and I will explain later. Yeah, it's a more complicated thing. So the first thing I want to say is that since we have four of them, right? We have AND or XOR and NOT, right? So we have four of them, and or NOT XOR. Right, so we want to make a reduction such that we remove some of them, remove some of them. Okay, indeed, XOR can be reduced to AND, OR, and NOT. Okay, so actually we only need an AND gate, OR gate, and NOT gate. The reason is that what's XOR mean? XOR means that one of them, if it's true, is that not two of them are true, but one of them is true, right? So simply speaking, you can just write this. This is one of it. So this is A or B. A or B. This is a not A and B. And this is N. So logically, what this equation means is that one of the condition must be true. A or B, right? So A or B must be true. But A and B cannot be true. Combine these two conditions, you get XOR, right? This is definition. If one of them need to be true, but not all of them, so not all of them are true. Yeah, so XOR can be used and can be used OR and then not, right? Okay, so that means that and or not, these three of them are enough, right? These three of them are enough. Okay, but indeed there is an idea called De Morgan rules. De Morgan's rule. So hopefully you guys know about this. So De Morgan's rule it basically says about following. It says that if A and B, if you take not, is the same as not A or not B. This is called De Morgan's rule. You can prove it by using logic, or I would say that you can prove by using algebra method. So I will describe it later. But ideally, basically, you can prove it. Or another way to prove it is using the Venn diagram, right? So for example, this is A, this is B, right? So A and B is this region. This is A and B. So not A and not B are all the shady region here. And then this is the same as not A, right? Not A are a region that not from A, and not B are a region that are from B. If their union are basically this region. So this is using a set theory or basically Venn diagram. So yeah, you can prove it. Okay. So this means that you don't need OR gate or you don't need AND gate. You can just use one of them. Okay. So that means that this proves that not an AND gate are universal. Okay. So algebraically, yeah, so I write a proof here. So N is, you can view N is basically algebraically just times, right? And A times B, and not gate is A plus 1 in modulo 2. And which OR gate basically not N and not B. This is the same as this formula. You change N and OR. And the XOR are basically also doable by my previous method. Okay, so this is just a proof that N or not is universal. And in general, you can prove that N and then not are already universal. Okay, but you can compose everything in one gate, right? Because you already know that N and not are universal, and then you can prove that there's an identical NAND gate. Only single NAND gate is universal. So this is the final results. NAND gates are as universal gate. Only single NAND. Okay. Right, so NAND gate can give you not A and basically not A and B. Okay. And then single NOT can be returned using the NAND of AA, right? You can check it. Okay. You can check it is true because if A is 1, then N of 1 is 1. You take a NAND, you take a NOT which is 0. Okay, which is not gate. If A is 0, then N of 0 is 0, but you take a NOT, which is give you you take a NOT which is 1, right? So NAND gate is actually can be served as not gate. So yeah, so N can be used just NOT and NAND. Okay, so this is somehow like I mean you don't need this because if you have NAND gate, then you already have NOT gate, right? Because NOT can be composed by a single NAND. Composed by, and then so if you want to do AND, then you can use NAND of not of NAND, but this NOT can be used in the NAND. So everything can be used using a NAND gate. Okay, so hopefully, hopefully you know the proof. Okay, so the NAND gate and NOT gate are somehow like, sorry, the NAND gate is universal, and you can prove the NOR gate as a universal. Basically, some exercise that you can try to prove it. Okay, so what I want to say is that for the classical circuit model, that everything reduced to construct an NAND gate. You only need some single gates, right? I'm not saying that this is the best way, right? If you have a lot of gate, that you can do things more efficiently. But what I want to say is that technically you can do this if you only have one. You only have the way to build one single gate. Okay, so I have an additional question for you. So we know that N or not is universal, and we find N is universal, and then we find NOR is universal. My question is that why N and OR is not universal? If you only have N and OR, why you cannot build a universal? So this is universal Boolean function. This is a question that I challenge to you guys. Okay, so I will stop here and make another videos.